cluster evaluation and supervised learning, and we will also talk about generative AI today, like start learning about what generative AI is. And this week, instead of dedication, I have a story to tell, and this is about once I started a startup, and from the drawing room of my house, and I engaged a few of my students. And one day, one of my students, he came to my house, and so I was working in one of the rooms, and so he came inside to give me something, and then he went out. And once he went out, he came back again, and he told me that his car is no more there. So his car was stolen. In like 3-4 minutes, he came in and out, and his car was not there outside of my house. So we searched everywhere in the vicinity, and we could not find it. So we went to the police station, and the police, the officer started writing the complaint, and he was asking about the make and type of the car. And he told him it was way back in 1998. Okay, so he said his car was Toyota, and model was 1976. Okay, so the police officer closed his register. He said, "Oh, go away, nobody is going to steal this car. You will find it somewhere in Westridge." So I was living in Westridge, so we started searching, and we found his car in front of racecourse ground. So the car was just parked there, and somebody took his tape recorder. So that's the only thing that was stolen from the car. So I was kind of surprised that the police officer kind of knew that this is the type of car which cannot be stolen. Nobody would take the burden of stealing a car of 1976 made. It was only 22 years old car. So that is really the human intelligence. And today we will see that how the artificial intelligence is doing almost the same thing, that you can figure out whether a car will be stolen or not. Okay, or somebody will take all the hassle of just taking it away somewhere, or just stealing something from the car, parking it at a place and stealing something and then just leaving the car there. So this is for today. So in week 7, we learned about, reviewed all the clustering techniques like k-mean, hierarchical, DB scan, spent quite a bit of time on GMM, and one of the reasons was that this leads us to understand generative AI. So that's why we should have a better understanding that how from given data, how can you basically model a probability distribution, a mixture of Gaussians you can extract from the data. And so that is something that we learned, and we could not cover Python. But I did share with you the thesis of one of my students. So and we could not also cover cluster evaluation. So for this week, I plan to just very briefly, I would like to discuss the generative Gaussian mixture model applications, and then that should lead us to discuss about generative AI. So that's primarily the aim, that to understand better and to understand the challenges. Perhaps we cannot just learn it in one class. So just to understand what are the challenges which people have been trying to solve in generative AI. And then we'll cover clustering evaluation techniques and what are these. And then from unsupervised learning, we shall move to supervised learning. That should lead us to understand deep learning and some of the latest stuff in AI. Then maybe, as I've been trying to just give you a very quick review of Python as well. So though I don't expect people to code in Python, but still you need to understand the algorithm which is being generated by generative tools. So with this application of Gaussian mixture model, there are many applications, and we also learned about the simplification of the covariance matrix, because covariance matrix is quite complex. So one simplification, once you have multi-model, means your data has many features, and once it has many features, see the covariance matrix becomes very complex to handle. So one simplification is that you normalize, like you have a standard normal distribution where sigma is equal to 1, and or you keep same value of the sigma for all the features. Okay, definitely you got to normalize the value. For example, if you have height and weight, they have different units, but if you divide it by the maximum weight and the maximum height, then everybody runs from 0 to 1. And then assuming that the spread is same as if you consider weight or height. Okay, so then once you are modeling, you will see your model will have a circle. So if the sigma is same for all the variables, the spread is same for all the variables, then the Gaussian distribution will be a circular distribution. Okay? If it is not, then depending upon which one is bigger, if your feature which is in the x-axis is smaller, then it will be something like this. Or if your feature in y-axis is smaller, a spread in y-axis is smaller, so it's about the spread. So because the width shows the spread, that the spread in the y direction and spread in the x feature. So whatever feature you are plotting on the x-axis, so it has a bigger spread. So it will, and once you have a relationship of a feature with the other, then you will see this tilting in one direction depending upon which is more dominant, which feature is more dominant. So we'll see that it will be a diagonal. So mostly, realistically, you are going to see diagonal features, but that will make a problem very complex to solve, and today we will see this as well. So as I mentioned, that you will find many application of Gaussian mixture model. One is in background subtraction, that if you have for the background, it has a different distribution usually of the grayscale, and your object has a different distribution of grayscale. So you can plot the distributions, the Gaussian distributions, and then you can decide that where you are going to put a threshold. For example, here it seems like that so it seems like that this is the threshold. So these are the image intensities. So seems like here is the object and here is the background. So by having a clear demarcation of the two distributions, you can decide that all the pixels which have intensity less than the threshold, you are going to just make them white, okay, or make them black, whatever. And the other part is your object. So you just do the background subtraction. So this is a paper where they have like successfully subtracted the background from the image using this technique, Gaussian mixture model. The other one is in image compression, where as you can see here, they have modeled it as this is the real image, and you hardly find a difference. And here is the same, but now it is modeled as 10 Gaussian mixture model. Here this image is modeled as 5 Gaussian mixture model, and as you can see, this is a bad quality, it's not a good quality. This seems like a good quality. Okay, as good quality means that once you are modeling it, so there are 10 Gaussians. So if you have one Gaussian and the other Gaussian and another Gaussian and the other Gaussian, so every pixel value has a center. So you go and this is the centroid. So you are going to have a centroid value and then add where it is on the Gaussian, and you replace that pixel with that value, replace that pixel with that value. So now every pixel in your image is truly Gaussian distributed. Truly means that you are only replacing it with the expected Gaussian value. So you find that you can very nicely depict a picture which is all Gaussian. Okay, so this is again another example where it is using 10 Gaussian mixtures, mean every pixel is within one of the clusters, and in one of the cluster it has some value, and so every pixel is replaced. So every pixel here is replaced by one of the 10 Gaussians, and you know that this pixel belongs to this because you have modeled it using their color. So what you do is that for every, if you remember, I told you, like if you have a RGB or a grayscale, so you plot all the grayscales on an axis and then see how many Gaussians you can fit in those grayscales, and for number of Gaussians. And once you have a number of Gaussians, that every pixel that you have placed on the intensity axis, you need to remember its location as well. So you say this is pixel number 2, 3 was in Gaussian 1, and this Gaussian has some amplitude as well, because this is what you have to compute. And then there is an adjacent pixel which is 2, 4, it is part of pi 2. Okay? So you have this mean, and wherever it is, so you calculate this value and replace the grayscale with this value now. Okay? It may be anywhere because you have fitted a Gaussian in it. So this is completely replaced by a true Gaussian. So every pixel is now Gaussianly distributed. And as you can see, there is hardly any change you see if you model it correctly. And that shall also help you to understand that if like even pixels are Gaussianly distributed, they make sense. So you can actually generate these images as well, because they are completely Gaussianly distributed pixels, which basically mimic almost the same image. Okay? So this also brings us to generative AI, where Gaussian mixture, because it's a model, it's simply not an assignment, and you have k Gaussian components, and based on this you can generate more data. So here is a paper, and I've taken this from the paper, and I will give you reference to that paper as well, that once you have so once you say Gaussian distribution, for every Gaussian you got to have all these parameters. This is the weight of the Gaussian, which we are calling in this paper, it is calling W, but we are calling it pi of j. Okay? So this is for the jth Gaussian, and this is the mean, and this is the covariance depending upon how many values are this, and this is for the jth Gaussian. Okay? So you have so this is what you need to find out from data. You got to find all the parameters. The parameters are usually written by theta. Theta mean all the parameters, which includes the weight, the mean, and the standard deviation. So once we say theta, theta mean all the parameters to describe the mixture of Gaussians. Okay? And x is your data. So from the data, you need to find out theta, and once given theta, then you can regenerate this. For example, here it says this is the data. Okay, so this is a paper which talks about the data, and they are trying to fit in Gaussian mixture into this. So they tried 2. Obviously 2 does not fit in well. As you can see, the distribution is like this, and Gaussian is like this. So there is hardly it is not fitting a Gaussian, because it's not in the shape of a Gaussian. Okay, so this is not a good fit. Then it went to having 16 Gaussian mixture, a mixture of 16 Gaussian. So as you can see, this is Gaussian number 1, this is Gaussian number 2, this is Gaussian number 3. It looks fine. Okay, so these are the mixture of 16 Gaussians. So this looks fine. This is called, so you got to find out the right mix of the Gaussians which can model your data. And even for this simple data, you need to have 16 Gaussians to rightly model this data as a Gaussian distribution. Okay, 16 Gaussian. And once you have these, now you can generate more data samples. And this is what it has done. It has generated 400 new data points using 16 Gaussian mixture model. So from here to here, there are 400 new data points which you can hardly distinguish. It seems like a same distribution, and this is what is important, that here you have lesser number of samples, and that's what people are doing to generate more samples. Then they train a machine learning algorithm on that data, because you got to have, especially for deep learning, you got to have many more samples. But if you don't have those samples, rightly modeling it with a Gaussian mixture of Gaussians, you can generate more data points. Okay, so this is the generative part of the AI. So now let's try to define the generative AI and how it is different from supervised and unsupervised learning. Okay. So we already have discussed this, that from machine learning perspective, you have unsupervised learning and supervised learning. Okay. So we have amply covered the unsupervised learning part less the generative AI part. Okay. And so this is in the supervised learning, we have labeled data. Okay. So supervised learning works on already labeled data. Labeled data means whatever sample you have, you know whether it is, if it depends upon the classes. So if it is a picture, you know whether it's a dog or a cat or a car or so you have every image is labeled. So and this is what you have basically learned from the past, and you have asked somebody who's an expert usually to basically label the data. So the data is labeled. So once the data is labeled, and then you have a new data sample, and then you try to basically learn through the labeled data, and then once an unknown sample is given, then you try to figure out that in which class that should fall. Unsupervised, you just have data. So you spend a lot of time in just converting an unlabeled data into clusters. Okay. So we have also learned this, that in unsupervised learning you have data samples and you feed it to a model. This may be k-means, Gaussian mixture model or whatever, and then if you want to, if you have a model, then you can generate more data. But in case of supervised learning, you have data and you have labels, because once you have labels, then whatever is the output of your model, you compare it with the label. Once you are training, and if there is an error, you feed this error to train your model. So the model usually is adaptive, it is trainable, so you train the model. So you have AI, then a subset of AI is machine learning, and subset of machine learning is deep learning. And so in deep learning, you have humongous amount of data. So deep learning usually it uses artificial neural networks and process more complex patterns, and where then you don't have to worry about the patterns. So we know that, and so many of these in deep means that you have many of these layers, hidden layers. So usually this is called, so we'll spend more time learning about this, but this is a hidden layer. And deep means that you have many of these, F1, F2, F3. So it's a concatenation of many of these layers, F1, F2, F3, Fn. So because you have many of these layers, that's why it is called a deep neural networks. And these are the classes, that it is a car, it is a bike, it is a shop, it is a traffic signal. So these are the classes. So we know that too. So generative AI is even a subset of deep learning. Usually, again, you require humongous amount of data to do the generation, and large language model is even a class of also deep learning that you generate a language model, and it is also a subset of deep learning, and we are going to spend time learning about the large language models. Okay. So generative AI is where you have this humongous amount of data and you find a model. So F is a model. So once you have a model, you can generate some output. So if non-generative AI, usually you have your output is number, discrete value, classes, probabilities. But in generative AI, usually you have natural language, you have images, you have audios, videos. So you are generating text, or you are generating images, or you are generating audio, or you are generating videos. Okay. So is also discriminative AI, where you are just splitting data into classes, and generative AI, you are making models out of your data, like we learned in Gaussian mixture model. So discriminative AI would tell, yes, this is a dog or a cat, but generative AI will create another picture of the dog, which is not in your sample space. So it's going to create a new sample, learning from all the data you feed in. It'll just create new samples, and so this is what the generative AI would do. So you have unstructured, unlabeled data, and you feed in. If it is a good model, it is going to generate new outputs. So these are the new content it generates, where for the unknown data, the predictive machine learning is only going to generate a label for the data you feed into a model. So this is very interesting that we have learned that somehow you can model the data using, for example, here mixture of Gaussian. And this is the work of one of MIT, one of Stanford graduates on generative AI. Okay, and he calls this score-based generative AI. Okay? And he compares it with even GANs, and he proves that his algorithm works better than GAN. Okay? So what it does is it's all about estimating probability distribution of data. So the whole generative AI is that somehow you got to estimate the probability distribution in the data. Okay? So for that you have to feed in a lot of data samples to your generative model. Okay? So for example, if you're feeding in animals or maybe just dogs, so you are just feeding all kinds of dogs so that it can model them correctly. So you feed in a lot of data, and now here is something very interesting to understand. For example, you have a picture which is 8 by 8 pixels. Okay, so 8 by 8 picture of dog. So if you linearize it, it is a vector of 64 samples. Okay, that's what an image is going to be. But if it is 1000 by 1000 pixels, so you can just imagine that the size of this vector will increase if you have high resolution images. So high resolution images becomes more challenging. If it is only a 2 by 2, if it is only 2 by 2 image, so there are only 4 elements. Okay, and we know if it is one dimensional, so we start with one dimensional, and one dimensional mean you have a value like from going, if it's an image, value is going from 0 to 255, and one dimension you just plot all the, every pixel is on this intensity axis, and you find out if there are multiple Gaussians, you will see that, and once you try to model it as a mixture of Gaussians, you will see all the Gaussians, that how well you can model this as mixture of Gaussian. So if you have modeled it correctly, you can add more, or you can have more data points from the distribution, as we were seeing that from the distribution by just, let's say I want to generate another 200 and it is a grayscale image, and let's say it is 256 by 256 image, and every grayscale has a location. So what I can do is that I can regenerate many of those images, making sure that they are from the same distribution. So from the same distribution, every pixel I take from the same distribution and the same spread, so I start creating more of these. Right? So if I have this 8 by 8, okay, so in this 8 by 8, for example, we have seen a 2 by 2. So let's say this is a 2 by 2. So in 2 by 2, as we can see that every pixel is part of a Gaussian. Every pixel is part of a Gaussian here. Okay, so every pixel is part of a Gaussian. It's a two-dimensional data. So a vector is a two-dimensional. A two-dimension means that still you require a covariance, which is sigma x square, sigma y square, sigma x, sigma y, and here sigma y, sigma x. Okay, so you need a covariance matrix, and you can generate more points. Every point in this image is part of a Gaussian. So if it is an 8 by 8, it is an 8 by 8, so it will, like a pixel, every image will be somewhere in this model. Every image will be like a point in 2 dimension, but now this is a complete image. Okay, and I have this Gaussianly distributed, and in whatever distribution it has a covariance as well with the other images in that distribution. Having this 8 by 8 means 64 matrix. So its covariance matrix will be 64 8 by 8. So 8 by 8 covariance matrix. So On this, because it is now 64 dimension, you cannot visualize it, but assume that every point here primarily is an 8 by 8 image. Okay, like here is a point, every point here is basically an 8 by 8 image. So in one Gaussian there are multiple images, in another Gaussian there are multiple images, okay. Those are part of this, and their covariance matrix is basically relating one image with all the other images in that distribution, because covariance is, if it is 64 values, then 64 by 64 covariance matrix, which says one related to the other, okay. So that's the complexity, that it kind of becomes very, very complex. So data distribution is unknown, and as we have seen that once you model it, that every point becomes part of a Gaussian, like we did it here. Okay, so here we said every point is part of a Gaussian. So this is where once you model it, so every point is a part of a Gaussian, it fits into the Gaussian. So what you do is, so this is all the images, maybe 10,000 of these. So these are 10,000 point in your sample space. If an image is just a 2D point, then there are 10,000 point in the sample space, and some will be closer to each other. Those who are related with each other, they will be closer together, and then you are fitting a distribution. May be Gaussian, may not be Gaussian. Okay, you're fitting a distribution. So the whole purpose is that you can, from here, you can derive a model distribution, which for this, just assume that these are Gaussians. Okay, so you have a model. If from the data, like you can have a distribution, so this is your model. And if you have a distribution like there, out of the points you have in a Gaussian, you can create more points, and in the entire image, so you can have all these Gaussians, you can generate more points. Similarly, in all these distributions, you can create more images by just sampling, because once you sample this Gaussian, if you look at this in 2 dimensions, so it will look like this. So you have some of the points are already there, and then you say, I want to create this point. So you find out its value in X and its value in Y, and you generate and you put it there. Okay. If you are going to generate 10,000, all the 10,000 points must be distributed across these distributions, and will one of the places that it will take. So similarly, I'll show you a simple example as well. So once you sample, okay, if you could correctly model, so there is a big question, that if you could correctly model, then if you take a sample, you will generate a new image. Okay, so these images will be very realistic, but they will not be from your sample space. They will not be the images that you have fed to the to this model. They are going to be a new sample point in the sample space. Okay, so he says this is one thing that you can do. The other thing you can do is you can put in an image and find out whether it fits into one of the distributions or not. Okay, if it fits in, you say it is highly probable that this image belongs to. This may not be an image from this data set, but you can say yes, this image looks like part of the model. So though it is not in the input data, but it will nicely fit into the Gaussians. Okay, so you say yes, it is highly probable. But if you given an image which will have, so this is a cookie, though it looks like a dog, but it will say no, it is low probability, it is not fitting into the Gaussians, because the model is very complex. It is all the pixels, the relationship with each other, okay, then the relationship with other images. So it's very, very complex model. Okay, humanly it is impossible that you have so many Gaussians and you fit them and train them. It's almost impossible. So it's even a simpler problem is also very impossible, where I'll show you what that problem is. But somehow if you can find out a model, it's a generative model. Okay, if from the distributions, if you can learn this distribution, it becomes a generative model. You can generate new samples. Okay, so this is what, if you remember, like theta are all the parameters. Like we said, the generative model is that you are given an x, given theta, you can generate an X, okay, because you are given all the parameters of the model. Theta are all the parameters of the model. That in that case, how many Gaussians are there and what are their relative contribution in making that model. Just an example which we saw where x theta was, where theta was every pi I, that how many of these are there and what is their mu I, what is their sigma I. Okay, this was the model. So so you say there are 16 of the Gaussians and there may be 1 million of these Gaussians, right, and their means and their this, okay, covariance matrix. So these are the parameters. So the whole purpose is from the data you got to have model of the probability distribution, which is all the parameters are there in the theta, which is this is what you have to find out. Okay? So from a sample space you take n samples and remember you randomly select from every class, you select few, this is what IID is, and then from there you find out all the parameters, and if you have the parameters then you have a model. So this is, and it should be very close, so this shows the distance. So p theta should be very close to the p data. So the probability distribution created by modeling it should be very close to the probability distribution that you have from the actual data, right? So that should be very, very close. Right? So if this is the case, you can, once you make a sample, just randomly select some value of mu, which is part of the distribution. So this is the mu1 that you are going to select. This is the covariance matrix you are going to select. So this will be a distribution in 1D. Select any point. Select any point. But this point should be with this much probability. So this is the point, and once you create this point, this will be a new point, a new sample point in the data that you have generated. So the issue is the data distribution is extremely complex for high dimensional data. If it is even for 2 by 2, we have seen like 2 by 2 data where you have like just points is pretty complex, like you were fitting 16, but if you have 3 by 3, it becomes in a volume. Once it becomes 1000 by 1000, so every point is 1000 by 1000, so it becomes very complex distribution. Okay, so it's saying the data distribution is extremely complex for high dimensional data, so it is not feasible, almost impossible to find out this distribution by fitting all the Gaussians, and so means that it's very difficult to make a model because to build a complex model to fit the data distribution, the model is going to be very complex. Even for a simple model, we make simplifications saying let's have every sigma same, or let's have no covariance, all the elements of a covariance matrix 0 except the one in the diagonal. So we are saying let's not even worry about a relationship of one image with the other. But if you are modeling, you got to worry about a relationship of one image with the other, and with every other image in that part of if you are fitting a Gaussian. And just think about the dimensionality of that, because if they are like 100 by 100 means it is 10,000. So a 10,000 dimensional, and if you calculate the covariance, it is 10,000 by 10,000 matrix. A 10,000 by 10,000 matrix where you have these diagonals and other elements which relates to every pixel relates to every other pixel kind of. So it becomes very complex model, and then finding out that how many of them are there and how many fits into, how many of these 10,000 dimensional vector fit into one Gaussian, which is 10,000 dimensional Gaussian, a very complex problem. So that's why people don't want to basically get into the nitty-gritty learning the maths, and that's what we did in the previous lecture, that we actually started with 2 Gaussian, then we started moving them and we fit them at a place where they appropriately fit in. Not possible, right? So that's the reason people start using, so instead here that you are trying to estimate all the parameters, and then it's a d-dimensional, and you are saying it's like a mixture of many of these. Even for one, you got to have you got to figure out the mu and the sigmas. So they rely on deep neural networks. Okay, they say it's humanly impossible for us to learn all these covariance matrices and the distributions. So they say let a network learns all of this, right? And end of the day, it basically gives us a model. Right? So all these weights, you keep feeding in 10,000s of images to this. They keep adjusting the weights, and then you say they give you a model. After many days of just the converging, they give you a model. Once they give you a model, means this model then you can use primarily to create more samples like these. So that's why deep neural networks basically are used wherever you don't want to spend your own brain on putting some math into the data. You say, let's not worry about it. Let's the network learns, and I have enough compute to basically make the model learn. May it take many days. I have enough compute, so people are relying more on compute, less on their intelligence. They are saying, let's not try even to be intelligent. Let's see, maybe it will converge, and it'll just create a model. And that's what they are doing with the large language model as well. Precisely almost the same thing, that they're just throwing a lot of data. There is a distribution. So every word you use, it has a distribution. So I visit, so a visit has now a distribution. Okay, so I visit Lahore, I visit this, I visit, and once I visit Lahore to see, now it has even more distribution, to see my parents, to see Badshai Mosque, to see Minar-e-Pakistan. I visit Lahore to see Minar-e-Pakistan, and now it understands it better. So it's all conditional probabilities, and these are probability distribution as well. Once I say I visit Lahore to visit or to see Shahi Mosque, and it knows that more probable is Minar-e-Pakistan, because that's what people, that is what it has learned that. So it's all conditional probability and a distribution. So every time you have number of a sentence, what comes next has a distribution, that which is more probable, and it's also Gaussian. So every time we have a word, okay, so here is a word 1, word 0, word 1, word 2, okay, and you want to find out word 3 given you have all these words, okay. So there is a probability distribution for, so you have word 1, word 2, word 3, and you are figuring out what is word 4 given. So this deep neural network has learned the distribution, that whenever these 3 words are coming together, so there is a distribution like this, Gaussian, that most probable is, if this is Badshai Mosque, Minar-e-Pakistan, then is a museum, then is zoo, then is this, then is parents, then is this, then is this. So it will show you the distribution. It will show you all the values which are in the distribution. So it has learned the distribution from the data, that if you are, so for large language models, it is primarily kind of this, that given this, there is a distribution, and it will, if it is generating it by itself, okay, it will automatically put, based on your prompt, it will put W4. Then it will bring W4 here and say, knowing W1, W2, W3, W4, given this, it will find out W5. Okay, from the probability distribution, it is going to pick the one, and does this stochastically, because if you run the same prompt again, usually it gives you a different answer, because stochastically it can just select some other. It will not going to give you, generate the same answer to make it more interesting. That, so it is not deterministic, that every time you give a prompt, it will not going to give you the same answer. It's going to give you a different answer, because that's how it is created. But it has learned all these distributions, and because it has learned, is add more. So if you see ChatGPT, it's just writing a word. So that's what it is doing. It's just keep collecting, and based on your prompt, all the data in your prompt, which is your query. So you have a query, it has a set of keys and values. Okay, so it matches it with this, and then it generates a value, which usually is, out of this is the next word, and the next word, and the next word. Just keep writing. and it do a little more than just checking whether the grammar is correct or not, and because it knows about your query, so this is amazing. People would not believe that it can actually produce something which is so meaningful and so impactful, and we will find out that it's not even words that are going in the model, it's just vectors and matrices, and the vectors are coming out without actually the algorithm ever knowing that what it is doing. It's just working on matrices and vectors and just coming out with another vector which basically is converted into a next word. Okay. So this is the challenge. So this becomes the deep generative model as well. So in the simplest sense, you trained it all the data you have, okay, and for all the data for this network to converge, it's not an easy problem, right? If there are 10,000 or 1 million images, for every image it has to come up with right set of parameters. If like there are texts, then every word, every sentence of the text, these weights are to be such that they point it to the next word, okay, which is there in the dictionary. So it's a very, very challenging problem. It's an intractable problem that how can just one set of weights, the weights are not changing, one set of weights can point you to all the possible distributions, okay, all the possible distributions if you are giving this. Okay. It's kind of almost amazingly impossible things to even think that, because these weights are not changing. Once you have trained them, these weights are fixed now. But now you have one sentence, it gives you the distribution of what should come. You change the sentence, weights are same, still it gives you a distribution. Now you change the sentence, the weights are same, and still it gives you a distribution which is relevant to what you have written. So no matter what you write, the weights will always give you the distribution based on whatever you have already typed in. So okay, so right, so this is the amazing part of generative AI, and which people are still trying to understand that how it is actually it works actually. And so now the challenge is, and this is what the people are trying to solve the challenge. बिल्कुल training data. So that's why they are just training it through trillions of words, sentences, stories. So whatever is there on the internet, they are training it on that data. So everything on the internet, and they are just increasing the window size as well. Okay, how many words back? It's a conditional probability. You say I used a word that I went to France, and then you are writing something. Then you say I went to see. It knows Eiffel Tower because you have somewhere said that I was in Paris. So it will remember that if you are in Paris, perhaps the most probable thing that you go to visit is Eiffel Tower. Okay? So it will generate that Eiffel Tower because this window, which is basically keeping all the previous words, it knows that this is the most, in the distribution, it is the most probable word. Okay? So it's just going to do that. And second is, we're just prompting, tell me something about Paris. The places I should visit Paris, for example. Okay, so now it knows that the people, because it has learned all the data from the internet, that people who have written that they were in Paris, so they went to see Eiffel Tower, they went to see this, they went to see this, and then the things about that. So it'll just start generating it. Okay, because it'll just take the prompt and then it'll just keep word by word. It'll just generate through the probability distributions it has learned from the internet. So because it has learned everything what is there on the internet, so obviously it has not learned anything good about us, perhaps, because there is nothing good about us on the internet, for example. So if there is nothing good about us, so it has no mind of its own. It has just whatever data you gave it, and it has learned the distribution from that data. Right? So if you ask it, I am an Australian, I want to visit Pakistan, so tell me something about Pakistan. So perhaps it'll say, take a travel advice first thing, you must take a travel advice, because it knows that anybody from Australia who is going to visit must take a travel advice, whether the advice is to visit Pakistan or not, because this is what it has learned from the internet. So that's another challenge, because there's humongous amount of data on the internet, and it's only the model, the distributions it has learned. It has no brain of its own, because it's just a probability distribution. It is just model, like mixture of Gaussians, you can think. If this is just mixture of Gaussian, it'll go to the right Gaussian and it'll just start generating it, that this is what it should just do. Okay, so amazing is the this network, which will point it to the right distribution, okay? The right distribution, and it has learned, so primarily all the parameters which can generate a new data sample. Okay, so it has learned the distribution. The issue with neural network is that this thing is not a probability density function. It is not a PDF. For a PDF, it is important, no matter what shape of PDF it is. For the PDF, once you take the derivative, once you take the area under the curve of a PDF, it is 1. Okay, so the probability distribution, your area under the curve must be 1. So, but what a neural network generates is not a PDF. Okay, a deep neural network generates is not a PDF. So the challenge is that to convert it into PDF, this is what they usually people do. Okay, and we are going to learn this more, but I'm just telling you the challenge. So the key challenge in this is to convert this distribution, which is not a PDF, into a PDF. You got to first take the exponential of this to make all these values positive, and then you got to normalize it so that it gives you, once you compute the area under the curve, it gives you 1. Okay, so this z of theta depends upon the covariance. It's a determinant. Remember, it is, you have the determinant of the covariance into 2 pi raised to the power something into this. So for the Gaussian, it has, you got to know, and that's the problem, that how are you going to know about the covariance matrix, because you know the covariance, only then you can find out its determinant. So the challenge is that z theta is where you got to have this exponential and this value, because once you integrate it, whatever value you get, you need to divide it by that. Okay, so for normalized Gaussian, where sigma is equal to 1, it is this value, 1 over 2 pi d over 2. But if sigma is not 1, then there is a sigma also here, 1 over 2 pi under 1 over 2 pi sigma under the rule. This is for the 1D case, right? And for the multidimensional case, it is 2 over d, and here is a sigma, determinant of sigma. For the Gaussian, if it is not Gaussian, then it even becomes more intricate problem. So it says it's an NP hard problem even to find out the normalized constant. So that's why people have been trying different things, and people are proposing different things, and this is what this guy, who is a Stanford PhD, has come up with a score based algorithm where you need not to worry about this distribution to always be a probability distribution function. So I have given a link to this as well if you want to go and visit. Obviously it's very complex at this point to learn. All I wanted to link it with what we have learned earlier, that if you have data, you can model it, and how you model it is, if it is Gaussian, you can fit multiple Gaussians. If you fit multiple Gaussians, then you can generate more data. Okay? And once the data size start becoming bigger and bigger, it becomes complex. Still, theoretically, you can have all these Gaussians fit into the data, and you can have a model, and once you have a model, you can generate more data samples, and once you generate more data samples, because now your data point is an image, maybe 1,000 by 1,000 image. Okay, so a data point means it is a 1 million dimensional vector. So obviously 1 million dimensional vector, it is very difficult to find out all the covariance matrices, all the Gaussians, and so it becomes a mathematically intractable, impossible problem to solve. And that's why people make use of the deep neural networks, and they say, okay, we have enormous compute. Let's try the neural network to converge and give us the model, the distribution. Okay? So that's what the problem is, and that's what this guy has solved. And there is another algorithm. So we'll just learn about these algorithms. There is one which is called stable diffusion. It has learned a model, and input to the model is a noise, a noisy image, which is a Gaussian noise. So you give a sample of a Gaussian noise to this model, it will generate an image. That's just amazing. Okay. So just noise you input to the system, and because noise you can always change, so just change the parameters of the noise, just generate a new model. With the same mu and sigma, you can generate infinite number of Gaussian noise images. So every time you have a new noise image, it is going to generate a new image for you. Change the noise, it will generate a new image. Okay, and if you have different types of images, sometimes generate a cat, sometimes a bridge, sometimes a flower. It depends it totally depends upon the noise, the characteristics of the noise. So this is what the stable diffusion would do. This is what his score-based method has done. All these images are generated. All these are generated. So this will also help us to understand. Okay. So if you look at this, this is an image of a cylinder, and many of these images. So this is my sample space. Okay. So if really the network is very intelligent, okay, so it is going to the model, the theta parameters, like we used to have theta parameters. Remember, we have pi I is how many of these are there, and what is the contribution of each. We have mu I, what is the mean of each distribution, and we have sigma or sigma I, which is the covariance matrix. These are the three parameters, and depending upon that how many of these are there, so you have set of these parameters for if you are fitting in Gaussian. So now the job of a good neural network is, spending no matter how much time it takes, generate a network. Okay, this is a neural network, and with minimum parameters should able to generate samples from the same sample space. Okay, and I'll show you the sample space just to understand it more. Okay, so for perhaps here it should able to just model it with two parameters, the minimum number of parameters which can describe all the sample space. One is the diameter of this or radius, and the other one is height. So these are the only two parameters. So if you have these two parameters, okay, and you say, okay, perhaps there are how many, and if it is discrete, even if it is discrete, okay, discrete means only it figures out these many are the diameters. So perhaps this diameter is same as this, okay, so this height perhaps is same as this and this, you know. So it finds out how many diameters and how many height. So it makes a sample space. So this is a sample space. Okay. So with two parameters, so given two parameters, which is out of this distribution, it has come up with 1, 2, 3, 4, 5. So there are 5 tuples. Every tuple has a diameter and height, right? So this is what the model is. So model is very simple, that there are 5 numbers for the diameter and 5 numbers for the height. Okay, so these are the 5 parameters. And once it has learned that given a D and an H, the network, this is the job of the network now. The job of the network is take diameter, take height, and draw a cylinder. So this is what the network is going to do. Okay, so the network has learned through its weights and through all the training that you have given it, all the training that you are just training, that is what you are going to generate. So this is something like this, where you have few parameters and it is going to generate an image. Okay, and you just give 2 parameters. So all these weights are definitely going to generate a cylinder. So for example, you give this diameter and this height, it will generate a new sample which is not there in your input sample space. All these are not there in your input sample space. Okay, so means the generative part of AI, if you have modeled it right and you have modeled the network right, given a sample, it will generate something which will look like that it is from this family, but it is not part of your input data samples. So this is called the sampling, that you are generating a sample in the sample space where that sample is not there, but once it generates it, it just looks like a cylinder. You say, oh yeah, it looks like a dog, it looks like a cat, but that dog, that cat, that person is not there in your sample space. So it has somehow, it has gotten into, and this usually is called the latent variable. Latent. Okay. So these are the magical variables, these are the latent variables. The job of a generative model is to find out these latent variables. Latent variables are called variables which cannot be directly measured otherwise. Okay. So for example, temperature in the sun, inside the sun nobody can measure, but somehow you can indirectly figure that out. So the latent variable basically characterizes something. Okay. Usually it is difficult to measure, and that's why you need an AI and a lot of computations to make it learn about this. So now to just summarize this part, and though we are going to spend more time, in generative AI, you are going to create a model. Model has parameters. If these parameters can be used to create another sample into the sample space, and the sample space is where your images are. So usually these parameters are fewer in numbers, as few as possible, so that just by changing those parameters, you create a new sample. Right? So there has to be like few parameters which should just able to make you generate, and those variables are called, or that space is called a latent space. That you are in a latent space. In the latent space, now you can create a sample, and the sample you feed it to the network will generate an image. It is the responsibility of the network or the generator net, like in GAN, it is a generator network which will do that. Okay. It also you feed in noise to a generator, it creates an image, you feed it to the discriminator, and then keep adjusting the weights so that the generator start generating things which are realistic. How it is doing this? By just learning the distributions. Okay. So that's what it is.